Hello and welcome to the session. I'm Dr. Akshay Kumar from School of Computer and Information Sciences, Indira Gandhi National Open University. And in this session, we will be discussing about solving recurrence relation, and we'll be discussing only two methods of solving recurrence relation in this particular session. For this presentation, we use recurrence relation to describe the running time of recursive algorithms. So we'll be not defining the recursive algorithms, but we'll be using the recurrence relations and how those recurrence relation for time complexity can be solved. Now, what is meant by solving a recurrence relation? Well, by solving a recurrence relation means that we are, after all, what is recurrence relation? Recurrence relation is an explicit formula, right, which is representing a term or the function onto smaller terms of that particular function, right? So our objective is to solve this particular, from the right hand side, remove all the recursive terms in that particular situation, okay? Or in other words, if we say, we mean that in this formula, basically, that Tn is free from recurrence term directly or indirectly. All recurrence references are removed. That is what it means to solve a recursive formula. Well, there are three methods primarily for solving the recurrence relation. We have already done in the previous session the basic way of solving was just by doing the iterative methods. We have done this particular kind of solution. But there are three important methods which are used to solve recurrence relations. The first one is called substitution method. So we'll be discussing about substitution method. Then we'll be discussing about recursion tree method in this particular session. However, we'll not be discussing about the third method, that is master method. In fact, we will be taking another session on master method, which basically is slightly more elaborate method, and we'll be discussing it in the next session. Well, let's try to do it with the help of substitution method. Let's define substitution method first and then try to solve a particular recursive recurrence relation with in terms of time complexity in using this particular method. Well, it is a two-step process. So substitution method basically is a two-step process. In the first step of this particular process, we guess an asymptotic bound to a given recurrence relation. So basically, we will be getting, our answer will be an asymptotic bond. That is, we will be representing it big O notation or big theta notation, right? So those kinds of notation ultimately basically are the solution to a particular recurrence relation as far as complexity analysis is concerned. And we will be then, as a next step, we have to prove that the chosen bound is correct using mathematical induction. So we choose a bound first and then we prove that this particular bound is correct. And how do we do that? By the process of induction. Induction is our very good friend, and we have already done one particular video on induction also, so you can go through that particular video first. All right, and we will take an example in this particular session to solve the recurrence relation, and the recursive or the recurrence relation which we have chosen to as an example happens to be Tn equals to 2 times Tn by 2 plus n. So basically, if you remember the last session, in the Tower of Hanoi, right, our recurrence equation was 2Cn minus 1 plus 1, right? Over there, what we were doing, we take a problem, okay, and we were dividing it into two problems, and one step was needed. One more step was needed to solve that particular problem, or one more move was needed. So number of moves were represented in Tower of Hanoi. Here, what we are doing, this particular thing is represented. Let's take this particular thing as that the first term, okay, 2t to the power n by 2 represents that our given problem is divided into two parts. For example, merge sort. Okay, so we divide the problem into two parts. Plus n basically is defining basically number of steps or number of moves or number of things which are required in addition to bring the solution of those two parts into a single part. So that is how this particular recurrence relation can be understood. Since the recurrence look closer to merge sort, right? This particular recurrence looks very closer to merge sort. So we may guess our solution to this particular recurrence relation as Tn equals to, or the solution as order n log n, right? That is what we are going to be assuming, and the base of this particular log is 2. Why? Because we are dividing the problem into two parts every time. Right? Now, this is a very important statement, and please mark this particular statement very, very meticulously. When we say a recurrence relation has an order n log n, what does it mean? It means that there exists a value c, okay, and c necessarily have to be greater than 0. All right? Please note this particular point. This is the meaning when we are dealing with the order, okay? C is greater than 0 such that Tn is, that is the value of the function Tn or the complexity is less than Cn log n for value of n greater than equals to n0. Let's try to recollect the big O notation which we have done earlier. So what big O notation was doing? It was representing the upper bound or the worst case of an algorithm, right? So if Fn, so Fn is the function for which we are basically doing the asymptotic bound, okay? And what we are saying that it is bounded by function Cgn, all right? Okay. So both Fn and Gn are two positive functions having a domain of natural numbers and a range as positive real numbers. So that's what you see. That is why the function, n is always positive, okay, n has to be positive all the time, and this particular function has a positive real number. Function has positive real in the positive quadrant only. That's what is there in the graph, okay, associated graph. Then Fn will be of order Gn, okay, so Gn is basically bounding the function Fn. There exists two positive constants. What are the two positive constants? One is C, another is N0, all right. So N0 is the point after which this particular statement is going to, Cgn is going to be greater than or equals to Fn, or in other words, Fn is going to be less than equals to Cgn, right? So that is what is the basic definition of upper bound, all right? So the same applies in this particular case. So what we are saying that there exists a value C0, right? Now here Gn in our case, with what we are assuming a solution, and that solution or order, we are assuming an order, right? And that order is n log 2 n. Okay, so Gn actually is n log 2n because this particular method assumes a solution, and since our problem is closer to merge sort, we are assuming this particular thing. Okay, but as far as the ordering, that is big O notation is concerned, right? There exists what it necessitates, that C has to be greater than 0, right? And Tn has to be less than equals to Cn log 2n for any value of C greater than 0, and for n greater than equals to n0. So we need to find the value C and n to prove this particular situation. All right. So let's use the substitution method in order to define this particular problem. So let's try to look into our function, okay, this recurrence function. Okay, so for n equals to 1, what is the value of this particular function? N equals to 1 case, because it is the Tn equals to 2Tn by 2, right? That was the function. And since n equals to 1, there is no half, 2Tn by 2 is, you cannot further divide it, right? So it is going to be, T1 is going to be just 1, all right? So as far as function says, right, Tn equals to 2Tn by 2 plus 1. So the terminal condition is T1 equals to T1 or equals to 1, right? While the solution is, okay, what solution which we assumed is that Tn is less than equals to Cn log 2n. All right. So what happens when we put 1, that is Tn equals to 1, what we get? 1 log to 1, and log to 1 is 0. All right. So what we get, T1 should be less than equals to 0. So this is not the n0 point, right? So T1 is not the n0 point. Probably n equals to 2 may be an n0 point where this particular thing gets solved. Right? So let's do it for n equals to 2. All right. So in that particular case, the function value, let's take the function value first. Tn equals to 2Tn by 2 plus n. That is our function. All right. So T2 becomes 2 times T1 plus 2. All right. And T1 is 1 as far as function is concerned. Right. So T1 was 1. So we get 2 plus 2 equals 4. Right. So T2, the value at T2 is 4. So and let us check our that is Cn log 2n, which why we are checking this? Because we have assumed that this particular recurrence relation can be bounded by with the order n log 2n. Therefore, we need to find the value of C at which this is greater than Tn. All right. So now here in this particular case, we are referring to the value T2. Right. So since we are referring to the value T2, so what is going to happen? So we are expecting T2 should be less than equals to C 2 log 2, right? Because we are replacing n by 2 in this particular case, and log 2 of 2 is 1, right? So we get 2C, it should be greater than equals to what we computed the value of T4, just computed with the function. So what is that value we have computed? It is 4. Or in other words, C has to be greater than equals to 2. And C is greater than, our condition was C has to be greater than 0, right? So we have got a value which is definitely greater than 0. Okay, let's once again try it for n equals to 4 also. Okay, why n equals to 4? Because it is simple. We are dividing, right, the problem. So it is easier to divide the problem into n equals to 4 means we will be referring to n by 2, that is 2. All right. So that way. Okay. So T4 becomes twice T n by 4, n by 2 is 4 by 2, which is 2. So twice T2 plus what n is 4, right? So we substitute the value of T2, which we have computed as 4. So T2 is 4, 4 into 2 becomes 8, 8 plus 4 becomes 12. So T4, the value of T4 is 12. Alright, let's find this particular value from Cn log 2n, which we have assumed, the assumed order, n log 2n. So T4 has to be less than C4 log 2 4, because n equals to 4 in this particular case. Okay, 4 log 2 4 is 2, right? So this is 4 into 2, 8. So what we get is 8C has to be greater than equals to 12. And once again, C greater than equals to 2 is going to satisfy this particular equation too. So we can assume, we can safely assume C to be 2. Alright, and now we have to do the induction step. So now once we have decided about C, so what we have decided about, two things. N0 happens to be 2, right? And we have decided about C. C has to be, let's say, take it as 2. It can be greater than equals to 2, but let's take it as 2. Alright. So now what we are going to assume? We are going to assume that this particular bound holds for n by 2. Okay, so what is expected in this particular case? T n by 2 is less than equals to C, okay, n by 2 log 2 n by 2, right? N is replaced by, Cn log 2n, that was the bound, right? N log 2n was the bound, now we have replaced it by n by 2 everywhere. Okay, now we need to prove, so we are assuming that this holds. Alright, that is what induction is. Okay, and we have to prove that it holds for n also. Alright, what was the case for n? It was, the function for n was Tn equals to 2Tn by 2 plus n. Alright, so Tn by 2 is going to, by this particular equation, is going to be, see, we are replacing it with the bounded value, C n by 2 log 2 n by 2. So T n by 2 is replaced by C n by 2 log 2 n by 2, which we have obtained from the, which we have written on the first line. Alright, and what we get, so n by 2, when you solve this particular thing, you get Cn. We further, log 2 n by 2 can be written as log n with the base 2 minus log 2 2, and log 2 is 1, right? So what we get when we solve it further, and the last term is plus n in any case, so we get Tn equals to Cn log 2n, okay, minus log 2 is 1, so it is minus Cn plus n. Right? Now C has to be greater than 0. Okay? Since C has to be greater than 0, so what we are basically doing, we are reducing some value. Okay? We are deducting some value. Okay? C has to be greater than 1. Therefore, what is there? It is going to be minus n plus 1 n. And C is greater than 1, so it may be 1.1, or let's say if it is 2, so obviously it is going to be minus n in the, if C is 2, right? Minus 2n plus n will become minus n. That means the Tn value is less than equals to Cn log 2n. Because you are, from Cn log 2n value, you are, subtracting some value, right? Based on the any value of C, right? So this is why Tn is always going to be less than Cn log 2n as C is greater than 1. Thus, solution of this recurrence equation becomes, now we have proved it now. Okay, we started assuming it, we proved it, we found out the value of C, right? We found out that there exists a value of C, then we assumed it for a value of n by 2, And then with the help of induction, we are able to prove that Tn is less than equals to Cn log 2n if it holds for n by 2. Alright, so that is the way we have proven this particular that the bound. Okay, so this is the substitution method. So we are able to prove that Tn is bounded by or by the big O notation as order n log 2n. So that way we are able to solve this particular recurrence. And what was the recurrence? Recurrence was Tn equals to 2t n by 2 plus 1. And it is bounded by, or the complexity of this recurrence relation is of order n log 2n. Alright, let us look into another method called recursion tree method. Now, recursion tree method is slightly simpler than our previous method which we have done. What was the previous method? The substitution method. Okay, the substitution method, however, required guessing a solution, right, which may not be always possible. Okay, therefore, a recursion tree can be used to make a good guess or even provides the solution. So it helps in providing a guess or sometimes even solution. Okay, so that is the recursion tree method. Well, the objective is once again to solve the recurrence relation using this particular method, and we are assuming the same recurrence relation which we have solved for the substitution method, that is Tn equals to 2t n by 2 plus n. Alright, so if I am saying Tn, so how I'm going to be representing this? I'm requiring n steps, right? So the tree is, please note the tree, right? First is the problem size is n, right? So basically n computation, n is the size of the computation because of the last step, n is coming over there, or you see 2t n by 2 plus n. So n is coming over there because you are joining two parts, right? Because it is 2t n by 2, right? So t n by 2 and t n by 2, these two parts are there, and we are taking n order time, or n is the time or the which is required to join these two, right? So that is what it represents. Okay, so 2t n by 2 we are representing, and we require n, to join this particular stuff. Okay, so let's divide, use this particular convention. This is the recursion tree. Let's use this particular convention to divide it further. So what happens? Okay, so we divided the problem into two parts, n by 2 and n by 2, alright, and join them, these two solutions using n steps. Okay, okay, so that is why the total n. Now, the problem with n by 2 parts will require n by 2 because we are starting with n, alright, and this n is the last n which is there in your recurrence relation, 2t n by 2 plus n. Had it been n square, we will keep it as n square, right? Okay, so in this particular case it is n. So what we are getting, n by 2 steps will be required to join n by 4 and n by 4 together. Okay, so n by 2 will be required for n by 2 and n by 4. So you are just further breaking down the problem till it reaches 1. And how many steps will be required? Okay, you can see on the left hand side, we have written it as log n base 2. Why? We are dividing the problem into two parts every time. This is very close to what we do in merge sort you do, or you even in binary search you divide the problem. But only thing is, in binary search you do not combine the solution. In merge sort you combine the solution in order n only. Okay, so this is how it looks like. So log 2n is onto the you can see leftmost side is a log 2n, is this the depth of this particular tree. Alright, and if I sum up the number of iterations or number of steps required or number of computations required, at the topmost it is n, then n by 2 and n by 2, once again it is n by 4, n by 4, n by 4, 4 parts now because n by 2 was divided into 2 parts, n by 2 was divided into 2 more parts, so now we have 4 parts. Right? So once again, if we put together, they will be n, and at the bottom we will have n parts, right? So that will be summed up to n. And how many of these? Log to n. How many? So we will be requiring n steps. How many times? Log to n times, right? So therefore, if automatically n into log to n becomes n log n, right? So the solution basically is we add the cost of all the levels to find the solution of the recurrence relation. For the recurrence relation, given this particular relation, cost of each level is n, which is plus n in this particular case, right? So cost at each level is plus n. And the longest path from root to leaf, how we are reaching? N from n to n by 2. Then we n 2 by 2 square, then n 2 cube, that way, right? So n by 4, n by 8, right? Basically, it is represented by n divided by 2 to the power k, right? And in order to know the depth of or the height of this particular tree, which is k, we will simply equate that we have reduced, from n, we have moved to 1. Right? So n divided by 2k has to be 1, and this will give us this equation is going to give us the value of k or the depth of this particular tree. Alright, so this particular equation reduces to that 2 to the power k equals n, which implies k equals to log to n. So at each step you have cost n, and log to n is the number of steps. So our total cost becomes n log 2n, and obviously it is going to be an order only, right? It is because that is what is in this particular case. Okay. However, we did not require this particular explanation of what we did in the substitution method. So with this we come, let's try to summarize what we have done in this particular session. We have computed the time complexity using 2 methods, right? For substitution method, where we guess the solution. However, the limitation was guess may not be possible for all recurrence relation, and in recursive tree method, it is not possible always, although it's a good, it is giving us a good solution. We are bringing down, we are breaking the tree, the recurrence into the tree, but it may not be very obvious in certain cases and may not be able to solve all kinds of problems, but still will give you a probable solution which can be used in the substitution method. In the next session, we will be discuss the third method called master method. With this, we end this particular session. Thanks for being here.